So now, um, so what I decided was I wanted to use this webinar as a foundation course for optics and give the best, what do you call, the best bricks and mortars, so that you can use that to build something very, very advanced. So the basics I'm planning to cover are some of the things that you'll be seeing in today and also in the coming webinars. So today's webinar, mostly I'm focusing on three key words. So you can say like these three are like are primarily very, very important keywords when and there is no optical imaging without these keywords. That is a lens. So you cannot have an optical imaging without a lens. You cannot do an optical imaging without a focus, and you don't have an optical imaging if there is no convergence. So the second term, the focus is somewhat, it's like a 50-50 scenario, because we say that an object is in focus and in out of focus. And out of focus, you still get an image, just that you cannot read any information out of it. But whereas for in focus is what is desired, because that gives a very detailed, sharp image with a lot of information. Good. So in this three realms of optical imaging, I want to cover four. I will be talking about four of these things. The first one is what is light in terms of optics. So light has like three definitions. So before we get into the slides, so the light is having three definitions. The one is the light is a Newtonian definition. That is a Newton's laws, a light which is based on Newton's law. The second is the light is based on quantum mechanics. That is the light which follows the quantum principles. And the third one is the light which is following the electromagnetic Maxwell equations. So the light that we all know, I'm pretty sure every participant in this webinar knows what a light is, right? So if I ask you a light, you will have definitely you will have a lot of things to talk about light. So, but coming to this lecture today, and these three most accepted definitions are from Newton's law, Maxwell's law, and the quantum laws. So these are the definitions which give very clear indication about light. And now for light to be used in optics. So whenever we are talking about light's use in optics, we are talking about Maxwell's light. Okay, so Maxwell's light theorem is the lights are electromagnetic waves. So that is what we will be using in optics along with some modifications. So we are not fully, we have to slightly change it a bit to design our cameras and use the light in building a camera. So we are going to see that. So that is the first topic, how light is defined in optics. So the second topic that we are going to talk about is the lens properties based on the shape. So you all have seen, like, if you have lens, when I say lens, that I am pretty sure, like, if I ask you what is the shape of a lens, you'll be telling me that it's round, okay, or it's oval, or it's circle. I have seen a lens, okay. So that is correct. That is one of the shape is mostly the lens are oval, or we can say spherical. That is the exact word that we will be using. Spherical cut lenses are the most widely used lenses, but there are also other shapes. Okay, so there are ellipse, there are parabola, there is sphere, there is circle. So we are going to see what are these shapes and how these, why do we need these shapes, because they have certain properties, mostly geometric properties. So you all know that a circle has a radius, a diameter, a area, and a circumference, all in formulas. A equal to pi r square, c is equal to 2 pi r. So all these formulas are known to us. So we are going to see how lens properties are defined based on their shapes. The third one is the focusing mechanism. So what is focus in imaging? So we all know a focus is, an object is in focus means it looks good. When an object is in out of focus, it looks blurry, it looks hazy. So that is the definition of focus that we know. But we are going to talk about in terms of lens and today's topic of optical imaging, what is focusing. Then the fourth topic that I'm going to talk to you is the convergence of light. So that is more like guiding the light. So the light, just like the lights are traveling, and we have to make sure that they reach certain destinations inside our optical imaging or inside our camera in order to have a feasible working prototype. Good, because the convergent, understanding the convergence of light is very, very important in building any cameras. So these four are the, I would say, like they are like the primary fundamentals that is needed for anyone pursuing a research in optical image. So now let's get into each of these sections and we'll see the details. So the first topic is about light in optics. So what we need to understand. So these are primarily, it's intended for whoever is listening must able to understand. So without too much technicality, we are talking. So I would say a light can be a bright light or a dim light. Okay, so we have something called as a bright light, and when I am telling a light is bright, it just means there are too many photons that are reaching us. Okay, so the too many photons are coming to us, and when I'm talking the light is dim, I just have few photons coming to me. So why I have put it in this shape, because what is the shape of the photon? It is no, this doesn't represent the shape of the photons. Okay, so what is the shape of these represents photon bundle. So each of these oval thing here represents a bunch of photons or a group of photons, and that is how light reaches you. That is how light travels. So in optics this becomes very important because we need to know how the light behaves. So the definition that we are going to take, the assumption for modeling the cameras is light consists of a bright light is a continuous signal or a continuous process, because these are samples. If you talk about these as excuse me, these as photon sample. Once again, probably people are having lunch and maybe just coming in. All are welcome, it's not a problem. So a bright light is continuous, and whereas a dim light is a discrete. That is one thing, but that assumption is not very, that's not very, do we need it? No, but do we need to? No, it's worth knowing it. But the second and third definition of light is very, very important. So now if you see, light travels in straight line. That is the first norm of deviation from Maxwell's theory. So Maxwell claims that light is an electromagnetic wave. So a wave, whenever I'm saying wave, just imagine the ripples or the waves of the ocean. So you all know that waves propagate. The ocean consists of waves, and these waves are not straight. They are like wavy, right? They are not anything other than being straight. But the norm that we are going to follow is the light travel in a straight line, even though, see, that is the catch, even though they are an electromagnetic wave. So what does this mean? So you're telling it is a wave and it is a straight line at the same time. So this is like a quantonian thing. Quantum also has certain this kind of contradictory things. Why light is said to travel in a straight line? Because the velocity of light is too fast, right? 3 into 10 to the power of 8 meters per second. So that is the velocity of the light. So the light travels so fast. So the light can go around the circumference. If you take an Earth, our planet Earth as a circle, the light can travel from one point. It can go around the Earth and come to the same point in 1/10 of a no, not one. I'm just, it's very few seconds. I was remembering some time back. It is like but it is very fast. So it will just go and come in like a jiffy. So that is the speed of the light. So even though light is a wave, and we are using that wave for our optical imaging or cameras, but to design such optical designs, we have to use the this thing. Okay, so we have to use the assumption that the lights travel in a straight line. So that is going to be the design criteria. So whatever cameras that we are going to design in the coming webinars, I'll be using the definition 2 very, follow it very stringently. So the third definition is the image is directly affected by the wavelength of light. This is also very, very important. So for image to come out nicely on the camera, you need a wavelength factor. So how these two? So we'll talk more on the third point in the next slide. So how these wavelength and how this straight line phenomena is going to help us, or it's going to be a factor that we have to consider when we are designing cameras for optical image. Okay, so to understand the points 2 and 3 that was shown before, we are going to perform a small experiment. So an experiment which has been proven study, it is a proven study. So the experiment is this. So what I have here is a hole. So I take a black cardboard. So the color of the I'm calling it black because the light cannot penetrate anywhere through the cardboard except through inside this hole. Okay, so I keep it in the path of the light. So let us say I have a candle or a torch. Something is, some kind of a bright light source is here. And now I keep it in the path of the light. And then what I see is the light, I get an image. So if I keep a sensor, so now we are only talking about an outside experiment, not inside camera. So let us say this is just a white paper. So it can be a white paper, but in reality, this has to be an imaging sensor. So you will see what you will see an image of this object on your sensor. Okay, good. So, and what I meant, the second criteria is satisfied because the lights are traveling in straight line and the images are getting formed. Okay, and they're converging. So the convergence will come next. So the focus is there. So when I say what is a straight path, this is the straight path, an arrow, because you may ask, it is coming from this side, that side, there are angles everywhere. It is not horizontal, it's not vertical. So what do you mean by straight? When I say straight, it can come at any angle, it doesn't matter, as long as it's not bent like this. So this is a not straight path, and these are all straight path. Okay, so now image is captured fully on sensor. The first one is it is a straight path, and the second point is that wavelength. So the wavelength of the light is smaller than the diameter of the aperture. Right? So what it means is the light wavelength, the diameter of the aperture is the size of this hole. So the size of the aperture and the wavelength. So the wavelength of the light should be. So if this condition is satisfied, okay, because the wavelength of, when I say wavelength of light, okay, very careful. You may think, so wavelength of light, velocity of light is high, wavelength of light, what it is. So what I meant to say here is your light is in the visible range, because it's an electromagnetic spectrum. We have plenty of frequencies. So your light is in the visible range, and this visible range light is what is being compared with this D. So which means the lambda less than and less than or equal to D means it is quite achievable. So you may ask, if lambda is too big, how it can be achieved, or it is too small, how it can be achieved. Yes, there are, because we are talking invisible. So always this lecture and all the research talks that we are considering are only for imaging in the visible range. So in the visible range, the wavelengths are very comparable, and this is very much achievable. Okay, lambda less than or less than D can be achieved. And what is the other case? The other case is where the lambda is greater than or equal to D. Right. So this is in that case, what happens is when this aperture is small or this condition is not satisfied, and we have the other conditions, that is lambda greater than the diameter and lambda equal to the diameter, and what happens is the light rays just don't reach the here, just don't reach the sensor to form your image, because the light has to. So that is your convergence factor. Okay, so focus we have not. The focus is the is still there, but now I've talked about what is light in optics, and now I'm telling why convergence is very important. So for every time you need to have a convergence, this is very much needed. This is a mandate. You need to have this condition satisfied in all your cameras. When you do the computation and when you do the design computation, you need to calculate this. You have to make sure that this is adequate. Then you can send lights through your camera, and then you will get a nice picture. Else you will not get a picture. So that is your convergence. Today's topic is about lens focus and convergence. All right, good. Now this is just optical image not capture. Next, light travel through optical imaging. So we have already said light travels in straight path. Okay, the light travels in the straight line, and that is something is given. Now what we are going to see here is few more things. Okay, so this is your typical lens. There can be multiple lenses used in an imaging system, but throughout this lecture we are only talking about single lens imaging system. So you have a single lens, and this is a light ray. So the light is penetrating this lens and it is going in a straight path. Okay, good. And now I'm going to call this area is your outside camera, and this side is inside your camera. And also the medium is very important, because here it is air and here plastic. Now the lenses are not made of glasses anymore, so they are made out of fibers, carbon, plastic. So they are made of this plastic, and then again you have air here. So this is a rare medium. I'm going to call it a dense medium, right? Plastic is a thick medium. This is a thin medium. Okay, good. So this is these are all the things we have to consider. And now what is the first thing I'm going to do is, whenever a light goes from a rare medium to a dense medium and back to a rare medium, there is a change in the speed of light. So light travels slow in water. We have studied the Snell's law, right? It is called as Snell's law in high school math, high school physics. We should all have learned. So it is the same thing. So, but we have to put in that factor when we are designing an optical imaging system. So which means the light travels from the air through the plastic and back through the air, and it reaches the sensor. So here is where you keep the image sensor. So here is where your image is recorded. When you click on the camera, when you press click on the camera, this will record something here. So, and that recording happens in this direction. So what will happen is, we have to put in the factor. So we have to consider the factor that the velocity of the light, if V1 is the velocity of light outside camera and V2 is the velocity of light inside camera, your V1 is always going to be greater than V2. Okay, by how much? That is your design goal. So now you have, this is just one lens, and if I have a refractive index, so we'll come to that. That is the most important derivation of today's class. So we can compute what will be the velocity of the light inside the camera. So I have two lenses, I have three lenses, then I can easily compute what will be, whenever the light passes through each of this lens, its velocity is going to reduce by a small fraction. So how much is the velocity getting reduced? And if I know that factor, what will happen? I know exactly where to keep the paper or where to keep the sensor that will record the image. Good, because the goal is to get a very good image on your sensor. So now when the light travels through different lenses, its velocity is going to change, it's going to slow down, which means it will converge to some place which is not uniform. Because depending on the lens material, lens number of lenses, the lens distance between the lens, all that will come. So depending on a lot of factors, this velocity, this v1 and v2 will vary. So we have to compute how much it's going to vary and where that sensor, where that image will fall on the sensor. Okay, so that is your v1 greater than v2. Okay, so that is the first point we have to take into consideration when we are designing our optical image. And this is also useful because we can design. Okay, I'll come to that. Next is the focus in optical imaging. So let me draw the same diagram. Now we are gonna. So I've talked about this velocity difference and how computing it will help in getting a best convergence and also placing the sensor at the right place. The next thing we are having is the focus in optical imaging. Okay, the focus is in optical imaging, what it means. So here everything is the same. This is outside camera, this is inside camera, and then the lights travel in straight line. So I'm keeping an object here. So what you see here, this is an object, and then what will happen here is whenever the light travels in straight line from the object and it reaches the lens, so the lens is going to do what? It's gonna reflect it. It's gonna send it through. Okay, it's gonna reflect and it's gonna allow the light to pass through. We want the light to pass through it because we want our sensor is kept at this side, so the light has to get through the lens and reach here. So in order to study what happens inside the camera, we can study what it means is because of symmetry in digital signal processing in many places, when in communication systems, how symmetry holds. So we have symmetry and we have asymmetry. So this is a symmetrical system. Your optical systems are mostly symmetric, which means whatever we are going to show here can just be duplicated, or it will be happening at the same locations on this side of your camera. Good. So what happens on the left hand side also holds true in terms of the distance and other things for the right hand side. So now the first thing I did was a ray comes here, then it is getting reflected, and second one is a ray which is going in a straight line, but it is going through this point, falls on the lens, and it is again getting reflected. Now the meeting point of this diagonal line and this diagonal blue line and this horizontal green line is your image. Okay, so this is your object and this is what is called as the focal point. So it is not distance, it is focal point. This is your image, and I'm just saying symmetry, so I'm going to extend the symmetry to this place. So in your camera, your image will be formed here. So this is inside the camera. So how I'm going to project it for symmetry is I'm going to take this line, then I'm going to draw horizontal here. And now if you see, you have seen this angle of incidence is equal to angle of reflection. That is what you see here, right? Theta I equal to theta R, something like that. So here, and this is the lens. So this property I'll tell in the next level. So this is how your images form inside the camera. We can rotate it because you may say it is inverted. Now there are mechanisms. You can plug in another lens that will easily rotate it and give you an upright image. So that and all is very possible. But now we are only focused on what is focus. So what is the definition of focus? Focal point is whenever the light passes through the lens. So whenever the light is falling on a lens, so what is lens? The lens is something that will allow the light to pass through or get reflected upon. So that is your lens. So mirror. So there is a distinction between lens and a mirror. A mirror is something where we call it as a silver coating. So a mirror is having some kind of silver coating, and it will be fully 100% it reflect back the light rays. Okay, so that is your um, okay, so that is your mirror. And now lens is what is the lens? When I talk about lens, then lens will be something that allows, it does both. It reflects and also it transmits, and that is mostly the angle of incidence and angle of reflection, refraction, all that is possible. So now what I'm talking here is the focal point. So whenever the lens we are using, then all the lens that we use in optical imaging or the lenses that go into camera follow this principle. So whenever the light reaches in a straight line, light comes in a straight line and falls on the lens, it will direct the lens inside our cameras, will direct it to the focus point. Any straight line that is parallel to this, let us say this is the principal axis, any straight line parallel to the principal axis will get converged at focus point, will get converged to this focus. Another rule of our lens is whenever a light falls, light passes through this focal point. So here, this is also a straight line. I told angle doesn't matter. What is a straight path and not a straight path we have discussed. So this is also a straight line and this is passing through this focal point. And whenever such thing happens, so here, whenever a straight light ray passes through the focal point and then reaches the lens, so it is passing through the focal point and it is managing to reach the lens, it gets what? It gets directed parallelly. So here, the lens is directing your light parallelly. So it's very simple. When a horizontal light falls on the lens, it gets diverted diagonally, and when a diagonal light falls on the lens, it gets diverted horizontally. Good. So this is the principle. This is the mechanism for all the camera lenses that you will see in the coming up webinar. So next webinar, we are going to show some real simulation on the software with these principles. So I'm going to show all this on the computer, how we can do. So that will also be interesting to see how these focusing happens. So the light when incident on lens always converges to focal point F. Good. When light goes through F, and so when light goes through the focal point F and falls on the lens, it gets sent parallelly. Okay. So this is the two kind of intuition things we need. We need this will hold for all this assumption. Of course, if you ask, is there any change to this? There is any way this can, yes, depending on the build of the lens, we can have a lens which is built, which will go at 2f. If you want to have a lens which will divert the light to 2f, then that also is possible. So this is something that, depending on how we build. So we are, what we are doing is, for our designs, we are going to use this. This assumption is what is given in the textbook also. So I was using this interesting book on optics. I have shared it in the group also. So that is a book I have taken these contents from. So that is these are the assumptions they are using for designing optical imaging for cameras. Okay, in camera lens system. So this is how you define. So here both your focus and convergence is mentioned. So here if you see, the focal point is where the light converges. So they are both the same. So the convergence point and your focal point is the same. And when it passes in diagonal, it just gets diverted horizontally. So this is very, very, very important slide and very, very useful when we design lenses. So the next thing we are going to talk about is the focus equation. So a very simple equation we will do, but this is not the equation we are interested in. So we are going to be interested in another equation that we will be seeing also in today's lecture. So I've told you how an image forms. This is how your object and image forms. Now, so this is the distance u, that is called as the object distance. V is called as the image distance. So this is inside camera, this is outside camera. F is your focal point. The standard equation is what you see in a very preliminary optics book is or even a physics textbook is 1 by u plus 1 by v is equal to 1 by f. Okay, so this equation is what you see. And now we will just do a small analysis on this equation. But can you tell this equation is not enough for our optical imaging? So when I'm talking about camera lens system, or we want to build a camera, then this is not enough. Can anyone tell why it is? Just a guess. This is the only question I'll ask the participants, so I will not ask any other questions. So this equation is insufficient in many terms. So I would say. So why is that? Any guess?
So because it is giving you the distance at a particular distance only, sir. The initial like mirror object position and the mirror, sir. If you change the position, the object, like, you won't get a sufficient answer, sir. Because focal length is only for fixed value, sir.
Yes. So okay, good. Okay, thank you. So that is partially correct. So what I think Ishan, right? Ishan, is it you?
So Tanish, sir.
Tanishq, yes, Tanishq, yes. It is good. Tanishq is this. Just I'm making it. Who is from the voice? So, yeah, what Tanishq said is correct. So there are certain limitation in terms of it's a fixed. Yeah, but why it becomes fixed? So it becomes fixed because there is no flexibility. This equation doesn't offer anything about the lens material, right? So you want to build, you want to build a camera, so you want to have a lens. So what is the lens specification? So that is not here. It only talks about the distance and the focal point. And the second thing missing in this equation is the refractive index. So we have spoken about the velocity v1 and v2. When light travels through different lenses, it slows down and the convergence happens at certain place. So that also have to be, no, it is not always the focal point. So that has to be considered, because when you keep a lot of lenses, so at the end of this at the end of this lecture, I have a demo, and that shows a very normal camera system. So a normal mobile phone camera system I have shown. So you can see, like, there are how many lens parts are there. So definitely, so here also, that refractive index, so the velocity of the light is definitely going to change, and there is no ways to compute that from this equation. So that is why this equation is not sufficient for our goals of designing an optical imaging system. But we will see some of the features of this equation. The first feature is what happens when u is infinity. So when I say u is equal to infinity, it means the distance of the object. So my object is at infinity. So what does it mean? It just means that object is at a far. It is not something, we can put it on the principal axis. So it's coming from a long distance. So this is what at u equal to infinity means. And u equal to infinity is always good, because what happens when u is infinite to this equation? So your equation becomes v equal to f, because 1 by infinity is 0. So it becomes 1 by v equal to 1 by f. So which means your object, or your image, will focus on f. So your image will get focused at the focal point. So which means or you can say, like, u has to be high. No, because infinity is something we don't know. It is not, it is something very big quantity. So you can just say that if u is large, then I am sure that I will have a very focused image. That is, if I keep my sensor here. If I keep my imaging sensor at f, then I'm going to get a very sharp image. So this design, or this equation, just tells us that. And this is not enough, because the velocity is not taken into consideration. So the next point is what happens when u is equal to f. So there are many cases. You will go. I'm talking about two. There are like 5 to 6 cases given in the textbook. You can just go. But these are the two things that we normally encounter in our practical designing process. So the second one is u is equal to f. Okay. So when u equal to f, so this means the object is placed at f. So when the object is placed at f, you tell this 1 by f plus 1 by v is equal to 1 by f. So which means u is equal to f. Then what happens? Your v is now infinity. Good. 1 by v equal to what? 0. V equal to infinity. So this will bring your image to infinity. So your image will not be anywhere here. It is going to be at infinity. So what does that mean? So where do we use that concept? So this concept is good. This is what we want. From a camera perspective, I'm very good. I'm very happy if I get one all the time. But even with few design changes, I'll be able to achieve this. And this is good. But two is something where the image is formed at infinity, and that is what how an image is going to be formed at infinity. So this is used. This mechanism is used in your far telescopic lens, magnification lens, mostly on convex lenses. Convex lenses where the magnification gets big and this image at infinity, because we need to then project a virtual image. So those are the cases. So this is like normal cameras, we can say. This for like microscopes, telescopes, etc. We will be talking about this virtual image. So we will not at this point we will not be covering this. So we will be, because here what happens is you keep the specimen. So you know where to keep the specimen. You keep the specimen at u equal to f, and then you get an image at infinity. And that the image at infinity is not magnification. So that is again, to be very clear, it is not magnification. It is just the image is at infinity. And when I project that image to a very far distance, then definitely I'm going to zoom the size. So the size is also, it's going to just get bigger and bigger, and that is your magnification. Okay, so that is what it is like correlated, the distance and the magnification. So that is what this is used for, and this is one. So this is the focus equation that we have. So we can, so which means these are the two extremes, when u is infinity and when u equal to f. So our designs, so when you want to write one paper, when you want to do some research and publish it, you can just plug and play, plays with these distances and see interesting things. You can interesting results. If you get, you can very well publish them. So that is what we. And mostly what this tells is that if we know where the object is, so if we are able to measure the object, then we will be able to tell the other parameters, this equation. Okay. So not much. So that much is good for that slide. So now we will come to this slide, 1 by v plus 1 by u equal to 1 by f. So this is the limitations I told. So the equations that is given here, 1 by u plus 1 by v equal to 1 by f, has a definite limitations. So the first one is the refractive index of the lens is not used. So which means the velocity difference, the velocity outside the camera and the inside the camera are assumed to be same, which is not. Okay, which is maybe for a very simple one lens it will hold, but not for advanced cameras. And the second one is the effect of lens curvature is also not considered. So I keep drawing these as the lenses throughout this lecture, and there is always this curvature can also be designed, right? It has to be designed. And how bifocal even our specs, our glasses work, right? The powers associated with that, so that has something to do with the curvature. So they so the same way, so how you have a power specification for your glasses, the same way these curvatures also can be controlled, can be designed for better sharp images. So just like our eyeglasses, how we wear them and we get a very clear view of things. So the same thing. Okay. So now we'll see this, how this equation is not enough, and we need to have more than this equation. So this 1 by u plus 1 by v is equal to 1 by f is not sufficient, and we are going to see how to improvise on that equation. So first let us see the curvature properties of the lens. Okay, so a concave lens, this is what a concave lens, parallel, it will converge to the focal point. So we have seen a convex lens, what it does is it diverges, but we have to project it to this using the symmetry. We have to project it, just this much is enough. We are only talking about the basic properties. Now these two are important, the ellipse and parabola. Why ellipsoids and parabolas are important? Because every time we are designing a lens, I'll show you. So what is the property of ellipse? So if you have studied ellipse in geometry, this is very important property. The ellipse says that wherever you keep, you take 2 points and you draw one line here and you draw one line here, and anywhere between this d1 and d2 will be the same. Sorry, d1 plus d2 will be the same. So the points are fixed. So what is the condition here? The points are fixed. So, and from that point, you draw a line to the ellipse, and then from the ellipse, you draw another line to that second point, and you can draw this in any manner. So you can draw it down, you can draw like this. I'm just showing 2 examples here. You can draw it in this manner. So when in whatever, the points have to be fixed, that is the only thing. So here we can say that our object is fixed. Our first point is our object, and our second point is our image. So you may say sir, what we are our object is not inside an ellipse. No, I'm just saying this is just to translate it to inside the camera. We can definitely do that. So it just means that d1 plus d2 is the same. So here also d1 plus d2 is the same. And this is a very important property of ellipse. So this gives us a lot of control in designing your lens. So the next is the parabola. So what is the geometric feature of parabola that will help us in optics? So in parabola, what it says is take a fixed point which is going through this parabola, right? And then draw one line to here, one line to the surface from this point, and then draw a horizontal line. Okay. Now what it has to be perpendicular. This line has to be perpendicular from this. Then what it says, what this parabola. So the parabola condition is the d1 will be equal to d2. Okay, d1 will be equal to d2. So this is one of the conditions of parabola. So these ellipse and this parabola are satisfying. So we have to put a plane here. So you may ask that d2 is not ending, so which means it can go to infinity. Yes, correct. But normally we keep a plane. So we are talking about imaging system. So let us say there is a sensor here, or there is an object here. So if an object is here and the light is coming from this, which means we can directly say that if it falls here, this d1 is equal to d2. I have put something here. So that is what it means. And it also applies to the image side. It applies to both outside and inside your camera. So this is a geometric property. So this is not something relevant to optics. It is already existing in the geometry. The d1 plus d2 is always a constant. It's always same for any 2 fixed points inside an ellipse. And also for parabola, the projection from a point on the horizontal is the same as the perpendicular drawn from the parabola. So these 2 conditions are very useful in our lens curvature. These are the only thing, right? So they are using one other design is ellipse, parabola, and sphere. So these are the 3 cuts normally we use for cameras for building the lenses of our cameras. So what I mean is used for building cuts means, now what will happen is we take an ellipsoid, right? So you design an ellipsoid, okay, and then you make a cut there. So you cut it in the front. Now that is your lens. So that is your concave lens. Understood? So that is your ellipsoid cut. And now you have a parabola. You take a small portion of that parabola, that becomes your lens. So that is how your lens get built, and it has certain distinct curvature properties. So depending on our design, we can give the specification and they will make this and give us the lens. Good. So ellipsoid, parabola, and also there is spherical. We can do the same with the sphere. You take a sphere, you can cut a small portion of the sphere, that becomes another lens. So we are going to see the spherical system in the next slide. Okay. So I'm hoping these are all things we need. So now why I'm telling all these points is so because next class I'll show you like how we can use this to build a very simple imaging system, and that is just a very fundamental imaging system. And you can, after that, there are aberrations and diffraction, lot of other things, all step by step we will do. So now for designing any simple imaging system, you need to know all this, so that you can set these parameters. You can just have to plug in these values in that software that we'll be showing, and then you get a full-fledged imaging camera. Okay, so we'll see that. So now coming to the last So it's 2, so we have time. So this is the last topic for the today's talk, that is refractive index of lens in camera image. So we have studied the lens curvature property, and now let us go to the refractive index of the lens. So before I was talking this equation 1 by u plus 1 by v is equal to 1 by f, and I was telling that that equation is not self-sufficient. Okay, so that equation is not sufficient for this because it's not taking into consideration the refractive index and also the lens curvature. So first I talked about the lens curvature property, and now I'm going to talk about the lens refractive index. So which means now instead of calling this distance u, I'm going to call it as u minus delta. And instead of calling this distance v like before, I'm going to call this as v minus delta. And now you have these two deltas, right? So this is this symmetry, let us say, and this delta is equal to this delta. Okay, and that is how I got it. Now n is capital N is the refractive index of the lens. So the plastic lens refractive index is capital N. Good. And now I've shown the ellipsoid parabolic cut in the previous slide. Here I'm going to use a spherical cut. Okay, so I'm going to use a spherical cut, and that is what is used in many, because the spherical cut, the radius is the same. So the radius is same because when I cut a sphere, it becomes a circle, and then again I cut a circle, I get a lens. Good, you understood? You can visualize it. So it's like taking a tennis ball, and you cut the tennis ball. What you see? You see a circle, and then you divide that circle into two, then you get two lenses, something like that. So yeah, so this is based on the spherical system. This is your radius r. So both ellipsoid and parabolic, another reason is both of them can be approximated into a sphere, so that is why we are sticking to the sphere. And another advantage, second advantage, is the uniform radius. So this makes, because what is the ellipse equation? Ellipse equation is, I don't know, parabola I know, it is y equal to 4ax, y square equal to 4x, something like that. So there are these equations. Sphere equation is simpler compared to these two, but there are designs with ellipsoid. So I just don't think that we have to use only sphere. You can use ellipsoid designs. You can use parabolic designs also for your system. So now this is, I'm calling this as my radius r. Okay, so this is my radius r, and then this is a perpendicular drawn from this point, and now my delta is, I'm calling this as the delta. Okay, because I am going to use this, I'm going to cut this for the lens, right? I'm going to cut two of this and join together, and I get this one. So that is what this delta is. Okay, so this is my this distance is delta. See, that is what this is. So what I'm showing here is, this is a big thing, and we are going to cut this, and we are going to make this lens. So that is why we are saying this here. And this distance, this total distance is r, and this small distance is delta, and this small distance is L. And now what I can say, my equation is r is equal to delta plus L. Good. Okay. Now let's come to this side. So I'm going to call this height h from the horizontal axis to the lens tip, and then I'm going to project. I'm going to draw two lines. Okay, let me do in a different color. Okay. And I'm going to, okay, Fermat light theory. What is it? Okay, quickly. I don't want to go too much into it. Maybe in another webinar I'll talk about Fermat's theorem. So Fermat was telling one thing. So what Fermat was theory is, let this, from this point to this tip be d1, and from this tip to this point be d2. They are the distance. So Fermat light theory states that the d1 plus d2. So here the light is going around the lens, and in this case the light is going through the lens, right? So the light can go inside, light can go through the lens, and the light can go around the lens. The Fermat light theory says that both are the same because the d1 plus d2 is a longer path, right? The distance from the distance d1 plus d2 may look longer, but the distance, the penetrating the lens is gonna slow down the light. So in the first case, d1 plus d2, the light is not entering the lens, it is just going around the lens. In the second case, or in the center of the lens, the light is fully penetrating the lens. So the Fermat's light theory states that both these are the same. So that is another property of lens. So we are talking about lens properties. So what are the lens properties that we have seen today? The first one is that the lens will, whenever a ray hits parallel, it will get converged to the focal point. That is the first one. And whenever the light ray goes through the focal point and hits the lens, it gets diverted parallelly. So these are the two things, ray guiding. Then the third one I can include in that too is the Fermat's light theory. A light penetrating through the center of the lens reaches the image in the same time as the light going around the lens. So in this case, this distance is d1 plus d2, and the light going through the center, this distance is u minus delta plus delta plus delta plus v minus delta. So Fermat's light theorem states that this distance and this distance are the same. Only thing here is, instead of just 2 delta, I have put 2 delta n. So n is the refractive index of the medium. So here all are considered. The lens curvature property. So this is the lens curvature property, and this is the refractive index. So this is going to give us a very nice equation that can be used for designing any of the optical cameras. Okay. So that is based on the Fermat's equation. We have this. Okay, and what does it mean? Light traveling through a medium and light traveling around the medium take the same amount of time. Okay, so when I say time, you must have, this question should come to mind. Sir, you're talking d1 and d2. You told d1 plus d2. So, and you're telling d1 is distance and d2 is distance, but you're telling here time. So what is time? Time is distance by velocity. So t is equal to distance by velocity. So here it is a light, so velocity of light. So that is c equal to 3 into 10 to the power of 8 meter per second. And that is the same, because here also the medium is light, here also it is a light. So everywhere you can put divided by c, that will give you the time. So it doesn't matter. So this is the Fermat's theorem. Light traveling through the medium and light traveling around the medium takes the same amount of time. Okay. There's plenty. Fermat's light, he has postulated a lot of hypotheses on light. Probably if time is there, in other webinars, we will definitely give 1 or 2 theorems, and because after this we will have a design. So we are only talking, the lectures are mostly from the design perspective. So this will help you in designing something. The next lecture will help you in designing something. Whereas Fermat's theory was mostly, it is theoretical perspective. So let us see how we have. So this is time is distance by velocity, and what is through is it goes through the center of this lens. Around means it goes around the lens. All right. Now this is our refractive index of lens in camera image. Now coming to the next slide, we'll take this equation, based on the Fermat's theory, and then d1 plus d2, and then time is distance by velocity of light. We have this, and this is something we have drawn in the previous slide. And now what is my d1? Okay, so Pythagoras theorem. So the d1 is, so this is my hypotenuse h. This distance is u minus, this is u, because I'm talking about the center. So this the perpendicular is at the center. So d1 is h square plus u square, and d2 is h square plus v square. Good, the d1 and d2. So we are deriving that 1 by u plus 1 by v formula. So we are deriving it again. But this equation will take into consideration all the factors, and this is a solid equation that we can use in our designs. So optics approximation. So the approximation that I'm going to show you. So the Pythagorean theorem gives us that root of h square plus u square, and now we are going to put in some approximation. This is an optics approximation. I have not seen it in any of the other texts where it is used like it's like they say like this is the approximation, and hereafter everything it's going to be used in this manner. So after that, in all the derivations they have followed this approximation. So that is why I'm calling it as an optics approximation, and this is given as this. So h square plus u square square root is given, I'm taking the u square common outside, and this becomes, when I take u square common, 1 plus h square by u square, the whole power 1 by 2. And now I apply this 1 by 2 to these powers, so it becomes u. And the approximation here is this 1 by 2 becomes 1 plus, this square root is given as 1 plus h square by 2u square. That is the approximation that we are using in this and in everywhere, wherever, because in the lens, a lot of times we need to use the Pythagoras theorem, because whenever you have a lens, you draw a perpendicular, and then you have an object, then you directly you get a right angle triangle, and when you have a right angle triangle, you can easily apply this Pythagoras theorem. And the approximation we have here is u plus h square by 2u. So which means the square root of u square by h square becomes u plus h square by 2u. This is the approximation that we are going to follow. So which means the first approximation is d1, and the second approximation becomes d square plus h square becomes v plus h square by 2v. This is equal to 8. Good. So now d1 and d2 has been derived. Good. Now what else is there? So we'll substitute. We'll just put this d1 and d2 in this equation, because here also we have it in uv terms, but here we have in d1 and d2, but now we have made it into uv terms. So let's put, and maybe I'll draw a line here showing, this side is the previous computation, this is the current computation. Then you just cancel it out, then see what it comes. You get in this manner. All right, okay. Now this is the equation that we got. Now what is delta? So we had made this equation delta plus L equal to R, because that was the spherical approximation, right? Delta is R minus L, and again we have a right angle here, so which means I can write my L to be what? L to be R square minus H square. This is H, right? So so this is my height, because this is the lens. I'm telling that I'm going to cut this and I'm going to use it as the lens. So the lens that you are seeing in the previous slide is coming from this spherical surface. So that means this height has to be the same. So this is now R minus L. L is R square minus H square. Here again Pythagorean theorem. So I'm going to make that optics approximation, and our optics approximation is telling me that this is going to be R minus H square by 2R. Excellent. So that will cancel out R, and then I'm going to get just H square by 2R. That is my delta. So I'm going to plug this delta in this equation. Then let us see, what do I get? H square by 2R n minus 1. Good. So now we are closing in on our equation, our optical imaging equation that sums up all the characteristics. Will come to this 1 by u plus 1 by v is equal to 2 by r into n minus 1, and that is your 1 by f. So before, where it was just 1 by f, now I am having 2 by r into n minus 1. The r is the curvature, so it tells about the lens curvature. Change the r, so I make this a different r, I get a different shape. Change the r, I get every time, I get, depending on the r, it's just like I said, the power of your glasses, the eyeglasses you wear. So just change the r, you get different curvature shapes. And then change the n. N is the refractive index, so that is the thickness of the plastic. So when I say n is 1, it's a thin plastic, and when n is 10, it's going to be a very thick plastic. So depending on the thickness of the plastic, your refractive index n will also vary. So now we have some control over the design. So I know that, okay, I can choose R and I can choose N, and I can get a lens. Now I change my R, I change my N, I get a different lens. And now I use these two lens. Now I want to see what my image looks like. So this way this equation is a very, very important equation for optical imaging. So we can model our cameras, we can model our designs after this equation. So you can apply this, you can choose few lenses by varying this R and N and calculating the object distance, focal distance, the image distance. You have a lot of things, in your hands now to build an optical imaging camera. Good. So I think that is our conclusion for this class. And today, what was the topic? So just to remind you, we were here to talk about lens, focus, and convergence for cameras. And I'm presuming, and I'm assuming that we have done exactly that. And I probably, if you have listened from the start of the lecture, you should have an idea of what a lens is, how lens surface affects images, what is focus, and how the focusing happens, the convergence we have spoken, focal point we have spoken, and also the convergence. So how important convergence is, and what are the things to do with it. And these equations are important because we are, for those who are doing research in optics, this will all be very much needed. So I think with that, it's 2:45, so it's good. 2:43, okay, we can close the talk, and I can take one or two questions, and then we can, and then I can go for lunch. I have not had lunch yet, so thank you. Yeah, I have a demo. Okay, I totally forgot. I told you guys I prepared a small demo for you. Yes, so the demo is shown here. What you're going to see here is a camera system. So let me just designed on using these whatever the concepts, because I'm also new as you guys in this optics. So I also started just recently in optics. I'm also learning and doing and making a lot of things. So hopefully soon we'll have some good productive output. So now if you see, now if you see this, so there is, okay, so this is typical, this is an automated design, and this is a camera design. So I've taken this as a camera design, which is pre-available in our software. And if you see this is a lot of lenses are there. So the different shapes, okay, just leave it. But this is all for focusing. For you can see that what happens is a light is coming. So this is a red wavelength. So it is coming, and you can see the direction is changing, and also the velocity will change, and then somehow it's getting converged to this point. And this is what we need to find: how a light can be directed, and how a light can be made to converge at a certain point. And when you do that proper, so you may think it is quite easy to do it. It is not. It is not, because you may have this focus, and you may have these two out of focus. Your image is still going to look degraded. So you need, this is a green wavelength and this is a blue wavelength. All three must be in synchronous, and all three must happen here. And then if you use just one or two lenses, if you remove, okay, this lens is there, that is why the focus is not there. I'm going to remove few of the lenses, then again your quality will be, because the light, whenever it passes through just few lenses, you will get the resolution will be very light. The spot diagram will be very weak. There are many, so this is something we need to learn. And what we have learned today is enough to just build a simple model, just like this. And this is a very simple system, and get an image. So you can use this to send an object. You can take a sample object in the software, and you can put it, and then you will see the image, and you will see that image is clear or not. How is the quality? How is all the parameters you can check to to judge the camera quality. So whatever your build, is it good or not? All that can be done. Okay, good. So thank you. So that is the demo I wanted to show today. I hope the lecture was informative. So if you have any questions now, maybe one or two questions we can take, and then we can close. Thank you.